So as we see here, we have our graph of net force versus acceleration. Net force is measured on our y-axis, acceleration measured on our x-axis. I'm actually going to go ahead and update this one here. Let's see, we got to get one more little thing to this. Let's add our units, make sure we have our units on here. So net force is measured in newtons. And we all know that acceleration is measured in meters per second squared. Awesome. Parentheses on there. Great. Okay, so now we look at this equation here. And as I'm going to show you on the board in a second, we remember that a y can go right in front of here. So we have y equals 0.36x plus 0.345. But as we see, there's quite a linear relationship between net force and acceleration. As net force increases, the acceleration increases in a proportional way. So we don't see any curved lines, like there's going to be a square in the equation, or any kind of inverse relationships between net force and acceleration. So let's go ahead and look at, if we throw this equation right here up onto the board, see what we can make of it. Okay, so this is the equation that we got from our graph. Remember that when we do equations on Google Sheets, it removes one variable. It doesn't put that y equals at the start of the equation. So you can always add a y equals to complete the equation. Now we have an equation, and if we look at it, we can kind of recognize that it's in y equals mx plus b form. So it's in slope-intercept form. So the first thing we can do is replace our y and x variables for what we have on our graph. So by looking at our graph, we recognize that we have net force on the y-axis. So let's replace this y with net force. And we measure net force in newtons. And we'll keep the 0.36 there. We get to x, and we realize that on the x-axis, we have our acceleration measured in meters per second squared. So we'll write acceleration in meters per second squared plus 0.345. Great. So we have a little more appropriate equation for our example. The next question is, let's look at this 0.36 here. And if we look at our y equals mx plus b, we notice that that must be our slope, because it fits right in where m does in our equation. We have to ask ourselves, what does the slope mean in this graph of force versus acceleration? Well, one way to really recognize it is to do a little bit of unit analysis. It's our slope. So our slope will always be rise over run. So let's look at our slope units. I'm going to write this, and I'm going to end up erasing it here, but slope units. Our slope units will just be the units of the rise over the units of the run. So the units of the rise are newtons, and the units of the run are meters per second squared. Good. Now, there's a little more expansion we can do. A newton is equal to, I'll just put colon since, is the same as a kilogram times a meter divided by a second squared. All right, so if we substitute that in for newtons, we will get a meter times a kilogram divided by second squared, all divided by meters per second squared. And you might be recognizing that you have a meters per second squared up here, and you have a meters per second squared down there, and they cancel out, leaving only kilograms. So we've seen that our slope has a unit of kilograms. So let's rewrite this. I'll keep that up there for now. Let's rewrite net force equals 0.36 kilograms multiplied by acceleration times meters per second, or in units of meters per second squared, 0.45. Great. Just remember that this kilograms comes from this simplification. I'm going to get that out of the way now. All right. Now we ask ourselves, well, what does this mean? What does this mean? 0.36 kilograms. Well, think back to our lab. I told you to keep one of our variables constant, and that was our total mass. And I asked you to keep your total mass at 400 grams, or roughly about 0.36 kilograms, right? There's a little bit of error because we did this with stopwatches. We had a little bit of friction in the pulleys. There were a lot of room for error, so our numbers are not going to be perfect. But this 0.36 is almost about 0.4 kilograms, or 400 grams. So this here is our mass of our system. So let's go ahead and rewrite this, and instead of writing 0.36, we're going to make it a little more general and say, well, that's just our mass. Because remember, we're trying to get to that relationship among net force, mass in kilograms, and the acceleration in meters per second squared. And the last thing that we kind of got to do is look at this number at the end. And it turns out there's nothing really exciting about this number. The only reason that it shows up is because of error. Again, there's a little bit of human error, a little bit of friction in the pulleys. Our number, this should actually, in a perfect physics world, equal 0. So we're going to ignore it. We're going to cross it out. We're going to blame it on the error in our experiment. So we are left with the net force in newtons is equal to the mass in kilograms times acceleration in meters per second squared. That's our relationship that we built from our lab. Now we can generalize it, and let's get rid of all the units and just say, in general, what is the relationship between net force, mass, and acceleration? And we'll see that the net force equals the mass multiplied by the acceleration. And that is our end goal. We have created this relationship between net force, mass, and acceleration. And this right here is in fact Newton's second law. That is Newton's second law. There's a proportional relationship between mass and acceleration that give us the net force. There's no squares, there's no curves, there's no inverse relationships. They have a linear and proportional relationship. And that gives us Newton's second law. One way you can write it a little more abbreviated is our net force like this, and that's equal to ma. So you may have heard in classes before that F equals ma, and this is in fact exactly where it comes from. And you guys were able to derive that from your own data. All right, so we just talked about Newton's second law, and we derived that the net force is equal to the mass times acceleration, or in an abbreviated form, net force, mass times acceleration. So we're going to start with an example. A 60 kilogram person is standing in an elevator that applies a 660 Newton upward normal force on the person. A, draw a force diagram. B, what's the net force? And C, what is the acceleration? Okay? A couple of useful things. Let's highlight some information from this. We have a 60 kilogram person, and they know that there's a 660 Newton normal force. Okay? So let's go ahead and draw a force diagram for this person. First, we know the person has mass, so therefore they must have weight. So we know there's going to be a force of weight. And remember, weight is just the force due to gravity. Now they have a mass of 60 kilograms, but remember, mass is not the same as weight. We need to do something to the mass to get the weight. And that's just simple. We multiply it by the acceleration due to gravity, which we're just going to call 10. So once you get in the habit of doing this, you'll see it's just going to be the mass times 10. So you can do a really quick calculation. Here we'll do it a little longer. 60 kilograms times 10 meters per second squared equals 600 newtons. So the weight is 600 newtons pointed down. We also know that there's a 660 upward normal force. So let's put that on there. F normal equals 660 newtons. Now notice we can't put any equality marks on this force diagram because we have a 660 pointed up and we have a 600 going down. So we actually have unbalanced forces. If there's unbalanced forces, that means there's a net force acting on the object. The object is the person in this case. So the question is, what is the net force? Well, think about it. What is the extra force in one of the directions in this example? We have 600 down and 660 up. So we can all see that the net force is going to be in the positive direction. There's more in the positive direction. And how much more? 60 newtons more. 660 is 60 newtons more than 600. So to see that written out, the net force equals the 660 newtons minus the 600 newtons and gives you positive 60 newtons. We want to make sure that we put the positive to say that it's happening in the up direction. We're calling up positive, down negative. Great, we found the net force pretty easy. We used the mass to find the weight, and we used the given force of the normal force. Now we have to use Newton's second law, asking what is the acceleration of this person in the elevator? Well, we know the net force is just equal to the mass times the acceleration. We know the net force from question B. I gave you the mass of 60 kilograms. Can we solve for acceleration? Let's see. So the net force is positive 60 newtons. And we know that's going to equal the mass of 60 kilograms multiplied by, we don't know the acceleration, so let's just leave it as A. And we say, can we solve for A? Can we isolate A? Well, all we need to do is divide both sides by 60. 60 divided by 60 gives you an acceleration equal to 1 meter per second squared. And the last thing we can add to this to make it more detailed is say it's not just 1 meter per second squared, but it's 1 meter per second squared in the positive direction. And there you go. That's our first example. Okay, example 2. A woman pushes a box across a frictionless surface with a 100 Newton force, and the box accelerates at positive 0.5 meters per second squared. Well, let's go ahead and say that this way is the positive and this way is the negative. Our person here is applying 100 newtons of force in the positive direction to cause this mass, which we don't know the mass. We don't know the mass in the positive direction. That's actually going to be our question. What is the mass of the box? Can we find the mass of the box just by these pieces? 100 newtons applied to the mass, frictionless surface. So let's go through and highlight some important things in this question. A frictionless surface, very important. No frictional force. 100 Newton push. And the box accelerates at positive 0.5 meters per second squared. So, as always, go ahead and draw a force diagram for the box to start off. So, we'll do it right here. We know the box has mass, so therefore it must have a gravitational force, or a weight. So Fg, as we saw in the last example, is just going to be the mass times 10. But we don't know the mass yet, so we can't actually figure out what this weight is. So we're going to leave that here. My question is the box accelerating down through the floor? No. Is it accelerating up into the air? No. But we know that the floor is applying a normal force to keep it from falling through the floor. In this case, the weight and the normal force are equal to each other. There is no net force in the y direction. No net force in the y direction. Now that doesn't mean that the box isn't accelerating. It's just saying it's not accelerating in the y direction. We see that there is a net force in the x direction because there's 100 newtons from the push, positive 100 newtons, but there's nothing holding it back. There's no friction. There's nothing applying a force in the negative direction. So our net force in the x direction is just positive 100 newtons. So no net force in the y, it's only in the x. And that x net force is causing this acceleration. So we apply Newton's second law. The net force is equal to the mass times the acceleration. Well, the net force is positive 100 newtons. Positive 100 newtons. And that equals the mass, which we don't know, so we'll just keep it as an m, times the acceleration of positive 0.5 meters per second squared. We just need to isolate the mass on one side. We divide by 0.05 here. We divide by 0.05 here. Anytime you divide by a half, you get twice as much as what you're dividing by. So the mass equals 200. And if we followed our units, we should get 200 kilograms of mass. So just like that, with a net force and an acceleration, we can find the mass. Okay, we're going to keep going off that last example. We found that our mass of this box that the woman's pushing is 200 kilograms. Now I'm going to ask a new question. We ignored friction. We set across a frictionless surface at first. Now I'm asking, what would be the new acceleration if there were 25 newtons of friction force? So if we go back to our picture here, let's get rid of this frictionless surface. Now there is friction on this surface, and it's applying 25 newtons of frictional force. Well, the definition of a frictional force always resists the motion. So we know that the box is moving this way, it's accelerating this way, but we're going to add a resisting 25 newtons of frictional force. 25 newtons of frictional force. So our net force is no longer going to be positive 100 because we have a resisting negative 25 newtons pointing in the negative direction. So we ask ourselves, what's the extra force in the unbalance? Well, we have 100 this way, 25 this way. We'll say that the net force is positive 75. Positive 75 newtons. Because this 25 takes away 25 from that 100 and just leaves 75 of extra. So now we come over here, we're going to apply Newton's second law. Again, the net force, which is now positive 75 newtons, is equal to the mass. Well, we found the mass of the box is already 200 kilograms in the last problem. And now we need to figure out what the new acceleration is equal to. Well, to isolate that acceleration on one side, we're going to divide by 200 both sides. And if we do 75 divided by 200, we're going to get an acceleration still in the positive direction equal to 0.375 meters per second squared. That is our new acceleration. Now we ask ourselves, does that new acceleration make sense? Well, when it was frictionless, it was 0.5 meters per second squared. Then we added a little friction, and the acceleration dropped to 0.375 meters per second squared. So that does kind of fit with our information that we would expect the acceleration to be reduced a little bit by the presence of friction. So hopefully this helps and is a good example for worksheet 5.